Good morning, everybody. How you doing? Everybody up early and ready to go? Okay. So as Vasan said, I'm going to try to give you some insights into the fundamentals of Monte Carlo and not so much the hands-on work that'll come later, but to give you an idea, as Vasan put it, of why intuition is not always a good guide and why we need mathematics and mathematicians sometimes. So let's get started. Here are the points I'm going to try to make today. First of all, the importance of Monte Carlo as a simulation tool. The simplicity, the deceptive simplicity of running analog Monte Carlo. I say deceptive because, as you'll see, there are a couple of options you might be able to try that won't be quite that simple. And in spite of the simplicity of the need for better methods, because analog is not very efficient in many applications. So we'll want to do better. And we'll look at some alternative treatments of absorption in analog Monte Carlo. So I'll explain all these things as we get to them. This is the point Vasan stressed, the need to confirm that the stochastic simulation that you're generating is faithful in some sense to the radiative transport equation. So you'll see that we'll develop an analytic model and a stochastic model and rigorously try to at least wave my hands at a proof that they're identical. And then last of all, and this is maybe the most important, the unreliability of one's intuition, at least if one is me. So it's good to have a healthy skepticism when you go into this business. Wrong way. As to the importance of Monte Carlo, it's important for a lot of reasons. One of them is that you can simulate just about anything physically, optically. You can make it work. You can't do that with lots and lots of most other methods, as a matter of fact. So it has a universal applicability that's very, very nice. The statistical error that we use is a very easy thing to generate. That's in stark contrast to what happens if you use deterministic methods where the error analysis is sometimes not even available. And certainly sharp bounds are not the rule, they're the exception. I think studying Monte Carlo is an intuitively appealing way to learn about light tissue interactions. And in fact, that's a way I learned about it a long time ago. Because you start with what is analog, and then you see it's inadequate in some cases. And if you're me, you get interested in why that's true and how to make it better. So you learn a lot about light tissue interactions, I think, by studying it. It's also useful, actually indispensable, I would say, for measuring the error or the accuracy of other approximations. And throughout this short course week, you'll hear about such things. You know about perhaps diffusion approximations or a higher order. P1 was mentioned yesterday. There's a PN set of approximations, deterministic. It's nice to know how big n has to be for it to be close to the transport equation. The higher n is in the Pn, the better it is for simulation of the physics. And I think in a way, this is one of the reasons that's most overlooked, perhaps. We can think of a Monte Carlo code and a computing laboratory. A laboratory is a mathematician's or computer scientist's laboratory. It's a virtual laboratory. We can run Monte Carlo experiments, and inexpensively and quite rapidly, we can do experiments with perfect repeatability and control. So, this is not an easy thing at all to maintain if you're working in a wet lab, but still, it's important. Now, the downside is all expressed right here. The accuracy of the Monte Carlo estimate, which is statistical, does improve as you improve the number of biographies you simulate. But the convergence to the limit is very slow. And it's at the rate of 1 over the square root of n, which tells you, among other things, that if you want to add a significant digit of accuracy to your Monte Carlo estimate, you'll need to multiply your n by 100. So, a square. And it doesn't take long to see that it's pretty tough to make the error come down to something reasonable unless you do special things. But in spite of all this, Monte Carlo experiments are the gold standard for validating measurements and estimating errors of approximation. It's universally used for that. And in fact, it's been the case for a long time, excuse me, that Monte Carlo simulations occupy a large fraction of all the computing resources in the world. There are many advanced machines that run nothing but Monte Carlo 24 hours a day, 7 days a week. And so they take up a lot of time. Now, part of that is because they're so slow. So that's not good, but they're important. Here's a bare outline of the talk. Start with the analytic model. Excuse me, let me get a little water here. So I'll tell you what I think the analytic model looks like. You've seen it already, really. I'll look at a couple of prototype problems that are being addressed by the biomedical community all the time. I'll try to introduce the stochastics in a kind of a slow pace, derived from the transport equation itself. We'll look at analog Monte Carlo, the simplest of them all, and then we'll look at some non-analog systems, discrete absorption weighting, continuous absorption weighting. These are alternative ways of treating absorption in an analog system. And then we'll get to the theoretical connections, and then I'll summarize and see if I can give you some summarizing take-home messages. So Watson told us yesterday that a lot of important problems can be expressed as a weighted integral of the radiance. So here L is the radiance. It's that six-dimensional dependence in R omega unit vector and time. And f is a known function which tells us where we'd like to collect the light. And that the L satisfies, I'm having a lot of trouble. I didn't think I had allergies, but I do. Here's the integral differential equation with full time dependence. And as an example of one such integral, we'll choose f to be a region in space, and otherwise it's one in that region and 0 elsewhere. So it selects this integral, which is the fluence. It's the integral over all directions of the radiance at a fixed time, and this is at a single position r. If you integrate this over positions of interest, you get the fluence rate in such a region. If you multiply that by the reaction rate you're interested in, for example, absorption, you'll get absorption rate in that region. So that defines the fluence, which is, as we say here, averages directional dependence. Actually doesn't average it, it collects it over all directions. Now, for simplicity, let's take a steady state case. So we'll set the time derivative to 0, and we're left with this equation, which is simpler. So what we can say is that this equation, the radiative transport equation, time independent, characterizes the solution of it, which is the global light field, the radiance, that originates from a physical source that's described by a function q as the light moves through tissue with these optical characteristics. So you give it the total, the sum of mu a and mu s, the total transmission coefficient, mu s, and p is the scattering, single scattering phase function. At a position r, it tells you the probability density for scattering from a unit director, omega prime, into another unit director, omega, on the unit sphere. Here, S2 is the unit sphere, the surface of the unit sphere, 2 dimensions. And the point to make is that this detector function, f, usually confines interest, instead of the light field everywhere, to collecting the light at specific and key locations. So that means that f will often have built into it a characteristic function of position and direction. Direction, for example, being described by the numerical aperture of a detector. So that's the steady state case. Now together, equations 1 and 2 constitute what we'll call the analytic model. Notice that equation 2 defines the full global radiance. Apart from fixing attention on a region where you want to collect light and make measurements. That's done in 1. So the first thing we might imagine if we want to build a stochastic model is that we'll have to use these 4 functions, q and the mu's and p. And we'll have to use f to localize the light. Now, once you've set this as an analytic problem, There are, of course, tons of methods for attacking it deterministically without using Monte Carlo. You can replace derivatives by finite differences. It gets you a discrete representation of the radiance at various points and directions. You can get a continuous representation using what's called the finite element method, which is a way of representing it as a linear combination of smooth functions that are locally defined. And you can convert it to an integral equation. We'll do that, and then use quadrature on it. And that's been done too. But as I said earlier, it's very hard to get sharp error bounds for these methods. And here we're going to focus, therefore, on Monte Carlo, for which the error bounds are easy to get in terms of the variance and the runtime, but they are statistical in nature. So it'd be nice to have probability 1, that is a sharp, rigorous error bound. We can't do that with Monte Carlo until we grind the error down smaller and smaller, and there are ways to do that. Here are a couple of cases that I wanted to mention. In the first of them, we have a virtual detector. So there's a region beneath the surface of the tissue and removed from the light source where we'd like to collect information. And the way we do that, non-invasively, is to use lasers and Monte Carlo to simulate it. Now this is reflectance, so this is you collect the light outside the tissue and not inside. And so we would say that we're distinguishing here between virtual, that is internal, and non-invasive external measurements with these two models, which are just little simple cartoons of problems that we'll encounter. And specific examples of some are these. This describes what's called spatially resolved diffuse reflectance, where we have a source at one location and a number of collectors, detectors at various positions removed from the source. So we collect light at all these locations on the surface z equals 0. And we'll assume here that there are no refractive index mismatches so that the problem is simpler. Otherwise, we would have to draw very much more complicated pictures of the way the particles behave. Now here, in a problem like this, it's interesting to vary the distance, which is called rho, between the source and detectors, because that controls the depth of penetration of the light. And it's also interesting to vary the number and locations of them, and specifically the locations which need to be placed strategically. That means with respect to sensitivity to absorption, let's say, and scattering. So you don't want to put them all in a cluster in one location. You'll need to space them so that one of them at least is more sensitive to absorption in the tissue, and another one is at the least more sensitive to scattering changes. Here's the representation of a weighted integral of the radiance in a time-dependent case. No, it's not. No, this is a steady state. We said z equals 0 in the integral, and we take the projection of each ray of light as it's entering a little aperture described by delta omega, and at positions rho, removed from the source, which are within a small delta rho of some center point, and that gives you the reflectance at this cross product in the product space. So in practice, you put the emphasis on a discretization of the tissue locally on the surface and capture the light that way. So that's an analytic representation of something the Monte Carlo can do. There's a temporal version of this as well that you'll encounter, and the reflectance here as a function of time looks similar and uses chunks of direction and time to get time-resolved measurements. In such a case, you need to introduce a pulsed light source, so it's a time-dependent source, and collect the light that arrives at a given detector at different times removed from the source. The times here are equivalent to distances traveled, and Vassan pointed this out yesterday. In a homogeneous medium, at least, the duration of the flight is very much like the total distance it's traveled. And again, you want to place your detections and your light distance apart strategically to get the sensitivity you're looking for. So sensitivity, the change, the rate of change of the measurement with respect to certain parameters, those are important things. We'll learn that later in the course. So to introduce stochastics in the beginning, there's another interpretation of this. Instead of a hard and fast analytic equation that represents a fixed solution L, the radiative transport equation describes the average behavior of a stochastically varying collection, a large collection of particles, which we call photons. That, in other words, it's varying with time, if you want to imagine a time variation here. But this equation then represents a mean population, M-E-A-N, a mean, the average population. So there's a variation in it, which is measured by the variance, and so on. So this gives a clue. If we want to use these functions, that we should use these functions, Q and the mu's and P, in order to introduce the stochastics. And that's just what the analog, I guess it's still too early in the day. Sorry. Here's how we do that. It's just not working today. Each photon each photon represents a unit of radiant energy that doesn't change throughout its life history, throughout its biography. The energy is conserved, which means either the photon is absorbed, reflected, or transmitted from the tissue. These are the only options. And analog biographies should therefore be generated by making use of these functions. So if we want to interpret that equation stochastically. Then we'll need to use the coefficients of the equation to get started with the stochastics. Carol, you had your hand raised?
I wondered if you needed a throat lozenge.
A what? Oh, are you not hearing?
No.
What you're hearing isn't good, but...
It's good stuff. All good stuff. I was just thinking maybe you needed a cough drop.
What's that?
A cough drop.
Oh, something to put in my...
A lozenge.
Oh, yeah. Carol and I carry these things around usually. Thank you, Carol. Let's see if it works. So we're introducing stochastics in this fashion. Let's see how we do it. We're going to sample. This little wiggle says that you sample starting positions and directions according to this probability density function. So the source function Q isn't normalized. Usually we normalize it so it's a PDF, probability density function. And we sample distances between successive collisions starting at r prime along the unit direction omega from this exponential distribution, which, a function which looks like a cross-section, a mu of any kind, e to the minus the same mu, that's already a PDF. If you integrate it from 0 to infinity, you get 1. And this one allows for changes in the mu t along the path from the position r prime to a position r. That's L, a distance L removed. So that allows for heterogeneity along the path. If you don't have it, if you have homogeneity, then this is just mu t e to the minus mu t times L, the distance, and reproduces the correct total mean free path 1 over mu t. So let's keep in mind, this is the transport part of analog Monte Carlo. This is how you get from one place to the next. It tells you how far to go and then what you're already along a direction. When you've gone there, you're going to make a collision of some sort. It could absorb the particle at the advanced position r with this probability, mu a over mu t, or it could scatter with the complementary probability, mu s over mu t. And if it scatters, the conditional change in direction, the scattering angle, whose cosine is described by the dot product of the old and new direction vectors, we usually call that, or sometimes call it mu 0. That's governed by the function p, which was under the integral sign. So here, let's see, we've used q, we've used mu t, we've used mu a, and we've used p, and we have a process for generating what are called analog biographies. This is that process, yeah.
So Jerry, I had a question. So in the radiator transport equation that you presented earlier and I presented yesterday, we wrote the single scattering phase function in a general way, P of R, omega prime going to omega. And here I see you've written it as a dot product. And so I just thought It would be useful to discuss why you're doing that in this particular situation and whether
Yeah.
we are forced to make that decision.
I'm not forced to do it. So the question is, why do we leave out the arrow in P that takes you from omega prime to omega? The answer is for simplicity only, just like dropping time dependence in the RTE. In the more general case, you can have lots of you can have processes, scattering phase functions that do depend on more than just the angle between the two. And so in cases like that, you'll want to write it in the more general way. So I've made it, rotationally symmetric here so that that isn't necessary, just to make the exposition clearer.
Sorry, I need the microphone. Sorry. So Jerry, it seems to me that there are actually two implicit assumptions you're making when we do that. One is that it's rotationally symmetric, but also that that you don't have an absolute coordinate frame that you have to worry about, right? Because it's just the angle of deviation rather than the absolute angle. You don't have to know your absolute orientation. You just need to know the deviation.
It's a local property. It's a local property, and so you don't have to know it, although R, of course, can take positions in different materials where the scattering law does change. Yeah. So is the point clear? There'll be cases that you'll encounter where you will need to have a more general representation of the phase function. And there's no reason Monte Carlo can't handle it. So I've just described a random walk process, I'll call it, which is a way of generating biographies from birth to termination. I'll call it the analog random walk, ARW process. And here's what it does. It generates a set of interaction points for each biography, little b, starting with the one at subscript 0, then going on and so on until it makes k collisions. And k here depends on b, but the notation gets complicated. It's not the same k for all. But it's interesting to show, in fact, and it is true, and it can be shown, that the number of collisions made by this process of generating analog biographies is finite with probability 1. So that means that the set of biographies that makes an unending number of collisions can be ignored in the measure sense. And measure is going to be an important characteristic. That's the case so long as there is some attrition in the system and no production. So if we have a positive mu A on a set of R that has measure to it, is kind of beefy and isn't just a point, then we'll have enough absorption to reduce the radiance so that the series that represents the radiance expansion converges, and that this measure can be defined with measure 1. It's a probability measure. So we don't have to worry about computations that go on forever to represent one biography. It's not a trivial matter. It's important to know that your computation is going to finish before you need your next meal. More generally, this is a special sample space, B, with this script is a sample space consisting of all such photon biographies. And the way in which we generate those biographies induces a measure, which here I'll call M sub an for analog, on that space B. You think of the likelihood function, if you will, the likelihood of generating, it's a density function, so you can't say the probability of such and such a biography is a number other than 0. What we say is the probability density comes from this measure. That's the sample space. The measure on it is induced by the process you use to generate the random walks. Here it's the analog process. And then to complete the probabilistic model, we have to have a detector, so we want to capture the light to correspond to the function f that we had in the analytic representation. That's done with a random variable, or we call it estimator or tally. It associates with each biography a number, a real number, which tells you the weight of the contribution of that biography. And we'll talk about some other than analog in just a couple of minutes. One of the drawbacks of Monte Carlo is that you can only estimate the error by statistics. That requires, if you have a random variable C, you take the average over capital N biographies B sub I of the value of their tally. That's the average tally after N such histories. The variance measures the square deviation, the sum of the squares of the differences between that N sample average and the individual sample representations. And the N minus 1 here instead of N is for technical reasons. If N is modestly big, it doesn't much matter, but technically we want to have it this way, which makes the estimator of the variance both consistent and unbiased. And then we take the square root. This is a second order kind of thing, and we take its square root to get the standard deviation. That's just the square root. So we have something which is comparable in a dimensional sense to the mean, and we can look at the relative error, which is much more meaningful than the standard deviation standing alone. And so we have ratios like this that give us a feel for the percentage error in the mean that the standard deviation tells you. Finally, because the generation of random walks and other features of the simulation have overhead expenses associated with them, some methods will take a lot more time than others, and so it's not quite fair to just use the variance of the calculation, which doesn't take account of the time expended. You multiply the variance by t. The variance depends on n of order 1 over n, so the variance goes down not like the standard deviation, 1 over root n, but 1 over n, and the time increases with n. So the product of these two is, roughly speaking, dimensionless, independent of n. That's why we define it this way. The smaller the denominator, the better off we are, and the larger is the efficiency. So we're interested in sort of maximizing efficiency if we could. Let me pause and ask if there are questions so far. Yeah.
Thank you. Can you go back over the part where you said the relative error is more meaningful?
Yeah. It's more meaningful because we want to know, sigma n is just a number, right? And as a number, it's comparable to the mean. And so if the mean is tiny, and the sigma is comparably tiny, that's not very good, is it? We want to know how tiny sigma is in comparison with C. So we take the ratio, the relative error, call that the relative error.
So it's like a coefficient of variation?
A coefficient of variation, you could think of it that way if you like, yeah. Mm-hmm. Any other questions? So far we've just talked about analog Monte Carlo, the statistical error analysis that's available to us. Okay, let's move on. Here's a movie. Thanks to Carol for that and for the cough drop, which seems to be helping. Really good. Yeah, this is okay, what we're looking at here, you'll see N on the lower right, I hope, and we're 1 millimeter removed from the source with the detector. And now we're increasing the distance, now we're decreasing the distance between source and detector, which moves the light field from right to left. Let's have another look at that. Here we start out with 1 photon in the random analog random. Now we got a 10, 100, 1,000, 10,000, now 100,000. Now we're moving the source detector separation from 10 millimeters down to 1. And the analog situation, you might have noticed, I hope you did, let's try it one more time. You might have noticed that when the source and detector are maximally distal, 10 millimeters instead of 1, you have less information available at the detector. It's a little hard to see. And even harder to make work. Okay, let's have a look. Now it's just building up the number of analog photons. The optical properties are those of cervical tissue. Here's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff. So you see that the light available at a distance of 10 millimeters from the source is much smaller than the light available closer in. Okay. That's an inadequacy of the analog generation, analog random walks. What do you need to make such a movie? Well, you have to input the tissue geometry and its composition. That means the dimensions, material decomposition. That means if it's heterogeneous, where are the homogeneous subregions? And its optical properties as a function of position, perhaps. A light source Q, which causes initial collisions that are transported from R prime to R along omega by this transport kernel T that I defined earlier. Here it is, again. Then the collision mechanics, which with probability mu s over mu t you exercise the scattering phase function to change directions. And there I have used the more general representation just to be inconsistent. Sorry about that, but there it is. And then this would generate the whole light field without a tally, without a function f. But then you do want to usually introduce a tally mechanism, which could be happens at escape or with a detector function that's either virtual or on the tissue surface. And so what we've done is moved from sort of the primitive analytic representation through functions like q, mu a, mu t, and p to ones that build up to operators that will enable us to represent this equation not as an integral differential equation, but as an integral equation. And the way we do that, now I'm waving my hands, this is a directional derivative. Hassan also mentioned that yesterday. It's the change in the light field in the direction omega. This is really not a partial differential equation. It's actually an ordinary differential equation along each direction omega. If you integrate along that direction, then you get an integral equation for the function L, which makes use of the operator K, which is a composite of C and T, and it makes use of the source S, which is related to Q through transport that we defined on the previous slide. So that means that this equation, putting in what we know to be the case for K, it's mu S times P times exponential in the more general case. That's the kernel in the analog situation, and this is the source. This is the once collided set of photons. So these source S has been moved from its position at the detector Q to a new position along a certain direction. So this is a first collision, and then there's all the other collisions here. And that integral equation is what we need to define the stochastic model. Well, to look at estimation, the simplest estimator is the terminal estimator, which tallies only on the final event of each biography. So if B is such an analog biography, the terminal estimate of reflection, say, counts 1 if the particle is reflected and 0 otherwise. If you generate capital N independent analog biographies, then their sample mean, which I called Cn bar on the last couple of slides, is this, and it just counts the number K of reflected photons out of the total N. That means that Xi sub T, this is the terminal estimator, it's actually a binomial estimator, if you're familiar with that. It's a 1-0 kind of estimator. That means if you square it, it's also 1-0. 1 squared is 1, 0 squared is 0. That means that its first moment, its mean, it is unbiased. It's easy to show that it's the probability of reflection. So if I take the theoretical expectation by letting n go to infinity, for example, here, we will approach the probability of reflection. Not too surprising. And in fact, because it's binomial, the expected value of every power of it is also the same probability for all m equals 1, 2, 3. We're going to use this property to show something in a minute. It follows from this that the variance of this estimator gives a relative error, which is the variance is p times 1 minus p, pq, divided by p squared, and the relative error takes the square root of that, divides by the mean, and takes the square root. That means that one of the p's cancels up and down. You're left with 1 here, and clearly this goes to infinity as p goes to 0. This tells you if the probability you're trying to estimate with a binomial estimator is very small, you'll have a lot of trouble getting a decent answer. So that means, in particular, if you put a detector really far from the source, signal is essentially 0 there. And so you're going to be in this situation where the relative error is very big, huge. The remedy for this that I'm going to prescribe here is to imagine that a photon is a packet of lots of photons collected together that suffer the same fate as they move through the tissue. So we'll start them with a weight of 1. Actually, the weight we start them with is just a scaling factor. It scales right through the whole computation. And that it's transported by the analog random walk process. So we're not changing any of the ways of generating the walks. What we're doing is looking at a diminishing weight at various points. We can do it either discretely or continuously, as you'll see. Here's the discrete analog, the discrete absorption weighting process. If you assign an initial weight of 1 in the analog process, that's what you do. It never changes. Instead, think of it as the starting strength is 1, and we're going to diminish this strength at each collision by absorbing a partial fraction of its weight, mu a over mu t at that collision. So particle moves. In the beginning it has weight 1, makes an interaction. At that interaction we apportion a fraction of it, we put it in an absorption bin, and the rest of it we scatter and go on. That describes another random walk process, DAW, and a new estimator, C sub DAW, which collects the weights. You can collect the absorbed weights, you can do various other things with it. That defines an estimator whose tallies are the weights. The characteristics it has is that every photon now leaves the tissue. None is absorbed. Fractions are absorbed, but the trajectory continues with a reduced weight. And so the trajectory never stops. That means it takes more time to run. However, you do get something for it. You get a variance which is reduced. And so I'm going to show you that now. Here's a sketch of the proof. With DAW, the possible values of its weights are 1, mu s over mu s over mu t squared, and so on. All the powers of mu s over mu t. Now, in the first place, it's clear and actually rigorously provable that the expected value of this estimator, which is the sum of all the powers of the weights, k, from 0 to infinity, times pk, which is the probability that a particle makes exactly k collisions before it leaves the tissue. So what I'm doing is actually compartmentalizing my space of biographies B into a disjoint sum of subsets, those that collide once in the tissue, those that collide twice in the tissue, etc. And then I make a sum like this with the probabilities of each clump, each component. That's P. That's P, the probability. That's the first moment of the DAW estimator, and it's also the same as the first moment, the theoretical mean of the terminal estimator. So if you count particles, let's say, that are transmitted, in an analog way, you get k over n for n of them. If you count the weights of n particles in the DAW process, you get a sum of different powers of mu s over mu t depending on the number of collisions they've made. And the theoretical averages of these are the same. So they're interchangeable random walk processes. You can use one in place of the other. Now, why finally does the variance of DAW reduce compared to the variance of the CT terminal estimator? Well, every one of the second moments for the weighted estimator is smaller than or equal to the estimate without the 2. So this is the square of this. When you sum that, you get something which is smaller than this, and it's smaller than 1, provided, of course, there's some absorption. So if there's absorption, you're going to get this result, because this second moment of the DAW estimator is strictly smaller than the second moment of the binomial terminal estimator. So that's true in all cases. I have a question in the back.
So I actually have a few questions here. First is PK probability, how many collisions you go through. How do you estimate that probability?
Well,
get the piece of case.
You could estimate it in an analog fashion by just counting the number k of collisions made by a whole bunch of biographies. That's one way to do it.
Doesn't that have its own stochastic error to it, though?
I mean, that'll have a stochastic error associated with it, that's right. Here we don't really care about it. All we care about is that the theoretical value of the mean is controlled by those numbers, whatever they are. There are certain cases where you can calculate them analytically, and there's some nice exercises to do in connection with that.
And that's helpful. And the other question is, since you have to take the photon all the way until it does something, until it leaves the surface, I mean, what happens if you're like going to a detector and it never hits the detector? Or
yeah, if you have a detector at the surface, for example, and the DAW particle weight never gets to the detector, then you won't get a response. And so,
but when do you know to terminate it? I guess. I mean, when do you know that it's never going to reach the detector? It's when it this case, when
it'll exit somewhere. Apparently, it will exit everywhere else but the detector. That's what we're saying, right?
Yeah, gotcha.
That's too bad. But it could happen.
Okay.
Yeah. Don't put your detector there. Yeah. Question?
Well, Jerry, I mean, everything you say is true, but it's only a partial answer to his concern. I mean, certainly there are Monte Carlo techniques that you can use to enhance the probability or to ensure that you only sample photon biographies that make it through a detector.
Yes, there are.
Location. So
There are. Yeah.
maybe that would
Yeah.
address
there
the
are.
question. So there are other Monte Carlo techniques that actually allow you to focus your attention solely on photons that leave a source and arrive at a certain detector that are much more efficient. But in this kind of very conventional, rudimentary, basic Monte Carlo simulation that Dr. Spanier is describing, just for the sake of establishing theoretical constructs, the unfortunate scenario that you're envisioning certainly
Yeah,
can't
some
be
of
the case.
the some of the processes that Watson's talking about now depend on what's called reciprocity for transport theory, where you can reverse the path. And so if your detector is very small and you want a lot of photons to hit it, start them there heading backwards and follow them back to the source. Now, if the source is equally small, you won't have improved your lot in life, but there are cases where you will. And cases where if you use both of them and the technique to tie them together in the middle, that you can get the result you want. Yeah, you had a question.
Yes, so with this method, you're taking off a known amount of weight on any collision. So if you know the path of a given packet, then you know exactly what's happening to the weighting. Is there any advantage to taking the weight off stochastically too? Because, as a single photon travels, or even as a group of photons travel, we would kind of expect them to scatter or be absorbed in a small area randomly rather than deterministically. So I'm wondering if this wouldn't mess with the mean, but would it mess with the variance?
Yeah, you can. There are techniques called Russian roulette, no longer called that, I think. But the idea there is at any point you can play a game of chance in which you terminate the photon with a high probability. And with the complementary probability, you continue it with an inflated weight so that the total process remains unbiased. So that's a way, in some calculations, it's a way of not spending a lot of computing time with very high weight particles. And instead, what you do is you split them into independent particles. That's called splitting. I'm sorry, if the weight is very low, you don't want to spend a lot of time. So if the weight falls below a certain threshold, you kill it with a high probability. With a complementary probability, you continue it with an inflated weight and go on from there. So in that way, you can maintain a range of weights if you like, and the variation of the weights about the sample mean is the variance. So this is a variance reduction technique.
But the actual change in a weight on a given collision is the same. It's, with the Russian roulette, I thought.
But you can change it.
Possibly.
No, you can change it differently if you like. As we'll see in a minute, you can change it continuously. So you can sort of. There's a combination of things that can go together. Okay. So that's discrete absorption weighting, and the variance is always better than terminal estimation if you have absorption. Here, with some fortune, good fortune, how do I make this full screen? Yeah, I'm going to have to. This is a movie not like the analog movie you saw before, but very similar in construction. We generate 100,000 random walks. Here we are at 10, 9, 8, 7, 6, and so on. And you can clearly see the better definition of the light field at the exit, at the distance of the, here's the start of it. Now we have n equals 1, n equals 10. Now we're building up the population of DAW generated photons. And now we're looking at rho as a function of the distance between the source and the detector. Yeah?
Are we only seeing paths? Are we only seeing paths which terminate exactly at the detector here?
No,
Then
we're not.
why is there, when it plays with the higher degree of separation,
I think that's
higher concentration right at the detector,
there is.
why would be more light in different places?
This is a good
Carol, do
question.
you have comments?
Yeah,
You made the movie?
so at the very beginning, of the movie, you're just seeing fluence. There's no detector involved here, except for there's the virtual detector.
Yeah, this is, okay.
But then a
good.
detector is added, and that's showing what we call kind of a probability of visitation and detection, where you do the full circuit from source into the tissue to the detector, and you see those paths, we call it the photon banana, if you will, that shows.
So
Yeah,
in
absolutely.
essence, I think what Carol's saying is it's a measure of the radiance at those positions reduced from the 10, 9, 8, etc. at those locations. And then you accompany that with the P of V and D. Yeah. So yeah, so what you do is you unite a forward and adjoint simulation so that you can represent a detector at those locations.
So should this be looked at, rather than one of these distributions be looked at as the likelihood of a given photon entering that leaves the emitter being at a given point at any time? Sorry. Should this be viewed as a PDF of the likelihood, given a space, that a photon will occupy that point in space on a path that goes from the emitter to the detector?
Yes, it is. Exactly. Good,
Okay.
Good observation. That's exactly what it is. It's a map from every position in the tissue of the likelihood that a full trajectory from source to detector will encounter that.
Okay, not a
And-
measure of pure
Yeah,
fluence at any given point.
That's right.
Okay, thank you.
Yeah, it is. Question.
Yeah, because you show us the two video clips based on I'm not sure if my memory is right or not, but when I saw the first just another way, then if the source and detector separation is 10 millimeters, your simulation looks it's very difficult to detect. But when I saw the discrete way, then if source and detector separations, but even though the separation is 10 millimeters, the simulation show me that the detector can detect the waves very clearly.
In the first case I showed, yeah.
So there is some difference to the first case and second case, but I think that all of the situation same, but looks a little bit different.
They're very different because there's the analog random walks terminate before they get to the detector, or they leave the tissue without encountering the detector. And that there's quite a few of those if the source and detector are quite far apart. Whereas every DAW photon leaves the tissue someplace, and through this device that Carol mentioned, the map that shows you which ones go all the way, you can see that there are many more, there's much more radiance at that position for position. Yeah. Now, the trouble is, it takes more time. So for that, we have computational efficiency, and we haven't accounted for that.
Yeah, if I might add a little bit. So my understanding is that in the limit as n goes to infinity, the map that is developed by DAW and the map developed by analog are identical.
Yes.
Okay, so even though the visual that you see makes it maybe appear that the result is very different in analog versus DAW, that's purely due to just the limitation that we ran. I don't know how many photons you ran, Carol, but 100,000 or a million or whatever it was. But I want to assure you that if you ran sufficient n, many more, you'll need to run many more in the case of analog than in the case of DAW, you will get the exact same map. The reason why analog looks so poorly, and you can appreciate that just by looking at the fluence maps, and you'll get to experience this in the lab today, is that given that once a photon experiences an absorption event, the entire trajectory is terminated at that point. And as a result, the amount of voxels that a photon in an analog simulation interacts with within the tissue is far, far fewer than the number of voxels that a photon biography interacts with in a discrete absorption weighting simulation. And as a result, the visual appearance of these density maps look much more grainier, much noisier, and with much more variance spatially, as well as the variance at any given voxel is much higher. Okay, and so I think that's a fair.
It is. It is.
Yeah, but I think that intuition, I think, is really helpful to kind of understand and realize. And I think you're going to go through continuous absorption weighting, which will provide yet different characteristics.
Yeah,
and
that's
you're
right.
going to be able
That's
to
right.
experience all of this in the lab this afternoon.
So you should think of these two methods, analog and DAW, as being, as generating identical kinds of biographies, except the analog ones can terminate anywhere in the tissue.
The reason why I asked the question, because in practical point of view, just source and detector separation is very important to detect the depth. But usually, just when I just conduct the experiment, it's not easy to measure the up to the 20 millimeters. It's very difficult to detect. But so I wanted to increase the source and detect distance. Then, based on my understanding, I think that if I increase the laser power, out power, I'm just wondering, is it possible to increase the source and detector separation if all of the specimen condition is the same, like the optical property is same? Then I'm not sure it's possible to increase the power. No.
You're asking about optimization?
So all of these simulations, if you saw on the previous chart of Jerry's where you take the mean value, so you actually divide all of the results by the number of photons launched. And so you're normalizing the results of the simulation to, say, a power of 1. And so these are more just to show how the variance changes with the number of photons that you run. It's not an indicator of actually putting in a physical power with so many photons in it.
Yeah.
Did I get that right, Wesson? Okay.
Yeah. So the point is that both of these techniques obey the transport equation. So if you let n go to infinity, you get the solution of the transport equation in terms of the representation of the radiance. And one is just faster than the other, but has a larger error variance. And the other is slower, takes more time, but has a lower variance. But they're otherwise equivalent. That's not the case for what I'm going to show you next. So, lest you think it's always that way, here's a nice chart that Carol prepared. It shows at the top, it's the logarithm of the, I guess it's the log to the base n, base 10, yeah, of the reflectance as a function of the distance in millimeters, I guess, from the source. And there are two lines here. One is red for analog and one is blue for DAW. So when you measure by means of a logarithm, you don't see much difference. If you take the difference of their relative errors this way, the analog minus DAW, well, the analog should always be bigger than DAW. I just proved that. And here's the green line that shows it is, and that the advantage increases rather dramatically as you move from close to the source to further away. So that's kind of lessons you can learn from doing these simulations. Now I'm going to talk about another method called continuous absorption weighting. This is still an alternative way of treating absorption in an analog simulation. If I say I can capture a fraction of the light at every collision, and then move on from there with the complementary weight, why can't I continuously reduce the weight? The light is, after all, diminishing, not discretely perhaps, but continuously, in which case it's easy to calculate what you need to do to the weight. So here's that idea. You again have a continuously varying radiant intensity. It starts with unit. You conserve energy as before. You launch photons with a weight of 1. And this is the weight you distribute in absorbed energy along a track of length s. So the complement of this is the probability of survival after traveling a distance s. And they're all computable easily because these are just whose battery? Is that anything to be I don't. I didn't bring it.
I have one.
For this?
Yeah. Continue.
Okay. Thank you. It's. Thank you. That's great. I guess I didn't bring it. Thanks, Vasan. Okay. So I said that this weight is easy to determine because the distances are exponentially distributed. And what you lose is with an exponential of mu a. The complementary weight then is scattered, and you can make change. Here I've again been inconsistent, omega prime to omega, this scattering phase function. Is that an unbiased method? If you use it in connection with the analog process. The analog process tells you that distances are selected from mu t e to the minus mu t s. How many think it is unbiased? How many doubt it? Yeah, you're right. You're right to doubt it. It isn't right. I'll try to suggest why It isn't unless you select the distances from mu s, e to the minus mu s d. The reason for it, sort of, is that as the light is diminishing continuously according to absorption, there's only scattering possible at any point. So the mean free path should be the distance between successive scattering collisions and not successive interactions of any kind. That's kind of the reasoning, but you know, that's intuitive, happens to be true. But it's summarized in this slide. If you want to reproduce the right mean free path, you should sample distances according to mu s and distribute the same weight along and the same weight scattered. That means that the distances that are correct in the simulation for CAW should be somewhat larger than the ones for DAW or analog. So to summarize on this slide, I don't think I need to dwell on it. You can generalize this idea very extensively and basically control the weights as you will, provided you make compensations in the generation of the random walks and the weights, and they go together. Make a change in the generation of the biographies, it's going to cause a change in the weights carried. So this idea is one that I believe Carol will talk about next. We use it in our perturbation Monte Carlo method, except there's a little twist to it there. But it's basically the same idea where you're using two different measures in order to accomplish what you want with one. Now here's a depiction. I like this one. Jennifer made this for me. It's a depiction of analog DAW and CAW fragments of biographies. So here's let's say a source. It introduces a particle at this direction in the analog case and makes a collision and goes on. And the color of along the line, it represents the weight of the photon. So analog, it starts with the weight of 1, continues with the weight of 1. There's no weight reduction, no diets for these guys. Now here's DAW. Remember, the weight changes at a collision, not continuously. So it starts with a weight of 1, just like this one, travels the same distance on average, and then it travels the same distance again with a somewhat reduced weight because you've taken away some weight at the collision point. But that weight then remains constant over the rest of the path. And here's CAW. It starts off with a weight of 1 and then fades more and moves along this color chart to show you that I'm constantly diminishing the weight, and it shows you also that the mean free path on average is bigger for it than for either of these two, because you've sampled according to mu s times e to the minus mu s and not mu t. Well, here's a summary. And this includes what I said before about PMC. So it's a method in which you model only scattering and account for absorption continuously. You can use it to collect absorbed light along each path. You can use it in the same way. Just make sure the simulation is done correctly. Am I going in the right direction? Okay. Here are some interesting charts that were made for me by Xuan Zhao, who is in our computer science department. These show, again, some differences between the three methods of simulation. What you're looking at here in the background is a collection of, I think it's 1 million random walks. So that light field was produced, I've forgotten which, let me take a look at all three of them. Okay, this is the analog one. This is the same number of random walks in an analog simulation. So you see not much information content here, even after 1 million, or maybe it's 100,000 random walks for analog. And then you have two that look quite similar. And one of them was produced by DAW, the other was produced by CAW. And then overlaying the cluster of random walks represented by the light field, there are 5 picked out that are special for that simulation. They're not special, they're just plucked out of the bunch. I'm sorry, I didn't have time to label these exactly the way and this isn't the right one either. Okay, let's just move on. Here for future reference, maybe I'm showing a contrast between weighted Monte Carlo and analog Monte Carlo, and the crucial step is right here for analog, where you can actually change, you can actually absorb the particle and then generate a new photon or scatter it and go on. And here there's no possibility of absorption. And notice the sampling is again different. Mu s here, mu t here. So I covered all these points already, but this is a way of indicating how the code would go. Okay, one last idea. The Neumann series. If z is a complex number, you probably are aware, if its absolute value is less than 1, that you can expand 1 over 1 minus z in an infinite series of powers. You learn that in beginning complex analysis. The integral form of the transport equation can be written in an operator way. Instead of L equals KL plus S, you write it as L equals the inverse of the identity minus K. And if K has norm less than 1 in a certain sense that I won't try to make precise, then again there'll be a convergent series of powers of K that represents the full solution. This solution is called the Neumann series solution of the transport equation. It is the indispensable tool for doing theoretical work in Monte Carlo. Here is the set of first collisions contributing to the radiance. Here's the set of second, those who collide once through S and then again with K, twice, etc. Add it all up. So this is that sum over K that I was using earlier, K being the number of collisions. And that means, in more detail, that L can be written as S plus here, first term, second term, and here's the general term, which is the sum over K, and K varies from 1 to infinity. because there are none that are ballistic here, none that are uncollided. So these are representing what's called the collision density. Okay, now this is the part that I can't really explain terribly well, but I'll try. To show that the analytic model is the same or equivalent to the stochastic model, well, first we notice the analytical model builds a radiance out of a source function Q or S and a kernel K, or pieces of it, and a detector function F. Whereas over here, the components are a sample space B of biographies and a measure induced from the way the biographies are generated, and a random variable that corresponds to what you're trying to capture. If you expand this function in its Neumann series, multiply by F, and integrate, you have on the one hand this representation of the integral. And now I'm going to try to convince you, well, suggest strongly, that what you're looking at over here is nothing more than this form of the integral. Because first of all, the measure can be defined on these disjoint subsets, one at a time. So the derivative, the differential that you take, can be written as the sum over collision numbers, and that's what this is. And what you're looking at here are the analog representation. This is an analog kernel now. It came directly from the transport equation. So if you integrate that term by term, you recognize that what you've just done is integrated the random variable with respect to the measure. Now that's pretty hand-wavy. The proof, you can find a proof in general, and I guess I have that on this chart, which uses a different notation. I apologize for that. The physical model, you have to have a phase space, the transport equation, the boundary conditions, and a detector function. The stochastic model with slightly different notation. B is the sample space. C is here the weight associated with the biography. And the radiative transport equation introduces an analog probability measure so that the expected value of this is the exact average value of C with respect to that measure, is in fact equal to the integral of F. You can find the proof, and this is one of the references in your handout. So it's hard to do that in an hour and a half even. But the take-home messages I would want to leave you with are, first of all, analog Monte Carlo is easy and very intuitive, and as I said at the beginning, deceptively so. Weighted Monte Carlos is usually a very good idea. There are other good ideas for improving the computational efficiency. Intuition is not always a reliable indicator of what's right and what isn't quite right. And the Neumann series is key to proving the unbiasedness of an estimator or the equivalence of the two models. And yeah, I thought this is the wrong set. I took this out just before I started today. But this says Monte Carlo is too important to be left to chance. That's a quote, a paraphrase of a quote from Bob Covey, whose name I had forgotten when I wrote this, Robert Covey, from a talk he gave saying, random numbers are too important to be left to chance. So with that, I thank you for your patience and attention, and thank my collaborators on this talk.
Thank you, Jerry. Questions for Dr. Spanier?
Yeah, one over here.
In the models, when trying to determine the angle at which it scatters, would the probability distribution would have been using the same me-related models that we were doing yesterday in the lab?
On my charts, you mean? Were they?
Well, so when you enter into a scattering event in some sort of random fashion, you have to determine, from my understanding, from a probability distribution, which direction it scatters. So
Yeah, the probability, the PDF P that I use is general. I just want to use the same one in the RTE that I use in the stochastic model. That's all. It can be general. Doesn't have to be Henry Greenstein. You could simulate me scattering with it, and so on. So you can use anything you can do in the lab.
Is there any sort of guidance that you'd recommend in determining?
I'm sorry?
Is there any sort of guidance that you'd recommend in determining?
As to which scattering phase function? Oh, that's a whopper of a question. Answer is not really. Henry Greenstein is very universally used. Me is useful always when you have particles that fit the description, spherical. When you have a distribution of sizes you can measure. And so if you want to be as exact as possible, in our codes that can use me, we do use me scattering. Boston might add something to that.
I think it really just all boils down to how much you know about the system that you're trying to model. So I think as to recapitulate Jerry, I think the one that's most pervasively used is what's called a Henry Greenstein phase function, which is a very simple phase function. Yeah. So the most pervasive is a Henry Greenstein phase function, which is a very simple one, but probably fairly well established not to recapitulate backscattering of light in tissues at large angles. So then you can go to more sophisticated me-scatter models, but and you got some experience yesterday in computing phase functions and scattering, spectral dependence of reduced scattering with wavelength for not only monodisperse but also polydisperse distributions. And often there are many papers that describe various tissue types as combinations of multiple polydispersed distributions using Gaussian or odd normal distributions. Further still, there's been a lot of work in expressing or representing tissue as a fractal distribution of scatters. And for those fractal distributions, you can derive still other phase functions. So I think given the power of Monte Carlo is probably the only framework in which it would be very simple to actually look at the potential impact of various assumptions with respect to phase function on using a virtual simulator to actually figure out what might be the impact of phase function on whatever measure that you might be interested in. Does that help?
Absolutely.